The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's webinar. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question, please use the question box on the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible throughout the webinar today. Also, today's webinar is being recorded, and a link to the recording will be emailed to you following the event. Please feel free to forward the link to people you know could benefit from this presentation. This webinar is brought to you by the Rely On product family, Next Generation Protection and Control. And our little message from our legal department: ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Today's webinar is Introduction to Substation Control Using Relays with JB Hicks. Jay is a Regional Technical Manager serving the Southeast region for ABB, located in Chattanooga, Tennessee. Primary responsibility is to support ABB's high-voltage line of protective relays and controllers. Prior to his work at ABB, Jay was a Senior Protection and Control Engineer at Tennessee Valley Authority. He was responsible for the protection and control design package consisting of calculations, drawings, interdepartmental interface documents, and construction assisting documents for substations and switchyards. Jay graduated from Tennessee Technological University with a BSEE degree and is a member of IEEE. Jay can be reached at jbhicks@us.abb.com. And it is my pleasure to introduce Jay. Jay, take it away.
Well, thank you very much, Tracy. Once again, this is JB Hicks, and I will be going through today with these objectives. Today we're hopefully going to review the manual trip and close logic and considerations for a power circuit breaker. We're going to review a capacitor bank, manual and automatic control. We're going to understand the control philosophy of using this automatic control bank control scheme and integrating manual control to that scheme to optimize the bank usage. And we're going to review a line breaker bypass scheme application. This scheme is a complex design involving instrument transformer switching that can be drastically simplified by using logic in the IAD. So in this webinar, I'm going to actually go over the logic that it takes to do these applications, and hopefully this will better help you understand the applications more and understand the logic and give you ideas on how to build on this logic. So we're going to start out with some easier applications like the manual trip and close of the breaker, and then go to more complex as the capacitor bank and the current switching scheme. So starting with the manual trip logic, for this particular consideration, the manual tripping of the breaker must be supervised by the remote local switch, and it must have the ability to trip the breaker locally by DMP. I'm getting some comments here. It's hard to understand me. We have some weather. I'm in Chattanooga right now. We're going through some storms, so I'll see what I can do, maybe talk louder or clearer. Is this any better? I'll try to speak louder, yes, and hold it closer to my mouth, I guess. Well, let's go over the manual trip logic. This is the logic you'll see in your relay and the logic blocks that are needed. Shown are two logic blocks, the SCSWI and the SXCBR. The SCSWI initializes and supervises all functions to properly select the correct apparatus. And the SXCBR is a model of a circuit breaker. It provides the actual states of the positions to control the apparatus. Inputs I've got going into this SCSWI is, you can see it, a QC Bay PSTO. The purpose of this wire tag is to determine if the relay is in remote or local. This will block manual control with the relay or substations in remote control and allow manual control if it's in local control. The next slide we'll be able to see how this wire tag is developed. And I'm sorry if y'all cannot hear me. I got cloud cover coming over here and some pretty bad weather, but I do apologize. The inputs I have going into the SXCBR are A and B fingers from the circuit breaker. This gives positive acknowledgement of what the circuit breaker is in. And we have an input connected to the SCSWI. This will allow external opening. It's connected to the binary input modules in slot 3 of this rely-on relay. It's binary input number 1 that correlates to 2 stud numbers on the back of the relay, studs 1 and 2 in slot 3. And we have an output coming out of the SXCBR. This is what will issue the external close command to the circuit breaker. So following up on how this logic determines if it's in remote or local, we first have to understand on the front of the relay there is a local remote switch. It's a push-button switch, and this push-button switch, based on the IE or the LED that is lit up associated to either the L or the R, will show if the relay is in remote or local. These lights can be controlled by this push button, or they can be wired externally. So what drives that local remote button, and here's the logic, is the LOC REM function block. This is tied directly to that push button. There's a setting in it to either tie it externally or internally to the logic. Here I have shown external connections to this LOC REM function block wired up to the inputs 6 and 7 on binary input module 3, driving this LOC REM. Based on the position of either the push button or external wiring, we drive a function block called the QC Bay. This will output an integer value, either 0, 1, 2, or 3, which then feeds in the SCSWI. Based on the integer value, the SCSWI realizes it if it's in local or remote. For DMP control, the DMP control will be based off of that same function block, the SCSWI. Here we're showing the tool of an example of placing the SCSWI, both open and closed commands on the TCP IP master number 1. You would select what controls you want and move it over to the desired master. And then you would change your index number to correlate to your control point list. So on manual control logic, some of the considerations that we need to look at is the manual closing of the breaker must be supervised by the remote local switch, and we see how to do that using the QC Bay command. We must have the ability to close the breaker through DMP, and we must prevent closing based on certain system conditions. These system conditions can be sync check or possibly some interlocks driven by ground switches. So your manual close logic that you'll need is possibly the input of an external close. Here I have a wired an external close to the input number 2 on binary input module 3. I've had a synchronization check element, and we're going to look in the next slide of how that synchronization check element is derived. And we have a ground switch. This ground switch is going to the SX-CBR to an input called BL closed. When this ground switch is closed, it will drive a logical output 1, blocking the operation of the SX-CBR. This will prevent any operation, any close operation of the SX-CBR. It will not block the tripping or the open command, which is shown right above it. And I also have an external close contact. This is the close signal will drive this close output labeled close PCB. I'm unsure if you can see my mouse. I hope you can, as I kind of use it as a pointer. So if we analyze the sync check you'll see in the logic is driven by the SESR SYN's ANSI number 25. And just for manual control, we're going to look at the manual sync output and the manual EN-OK output. These outputs are what's going to drive the manual sync is OK. The reason you need both these outputs is the manual sync OK will be looking at conditions of the line for dead bus, live line, dead line, live bus applications, and live line, live bus, and assuring that you're in sync on both sides of the breaker. You'll need the manual EN-OK for the condition of a dead line, dead bus condition. This is if you're testing the breaker with a dead bus or dead line, and you want to allow close operation. For your manual close logic, to associate this to the HMI control, I'm depicting a circuit breaker on the HMI screen and associating it with the SESWI. This allows you to select open and select close the particular apparatus you want to control. So now we got some basics on opening and closing logic. We're going to go look into a more complicated scheme. This will be about capacitor bank protection and control. We're going to look at some key control elements and analyze some of the logic that was used to do these particular control functions. This particular capacitor bank is based off of a differential voltage protection and is based on a particular user's preference. This customer-specific application shows some key control aspects of the 670 or rely-on relay. So to get a general overview of what this capacitor bank is going to do and the controls that were needed, let's look at the single line of this capacitor bank. The differentials that are going to be protecting the capacitor bank are going to be individual to each bank. It will have its own differential element able to look for shorts in cans or can failures. Pretty straightforward protection. The key we're going to focus on today is the actual control aspect. And with the control aspect, we're going to have to develop some certain conditions that we will see this capacitor bank in and act on those conditions. With those conditions, I'm going to have to define some voltage levels that I want some action of these circuit switchers related to these capacitor banks to either open or close, adding bars or taking away bars from the system. Based on that system voltage, I will associate it to different voltage levels, which I'm going to call the 27 or 59 wideband, 27, 59 narrowband associated with the NB, and some 27 dB or dead bus condition. With these different voltage levels, I'm going to have to define logic to either open or close these particular circuit switchers associated to these capacitor banks to stabilize the voltage. All right, for the existing solution of these controls, the following control solution was achieved by 4 logic controllers, 5 voltage transducers, and multiple control switches. We're going to show all this done based on logic inside the relay. So to find our measurement values, here I'm repeating what I said when we were looking at the single line, is we're going to have to define the wideband over voltage, wideband under voltage, narrowband over voltage, narrowband under voltage, and a dead bus condition. The manual control of these circuit switchers have to be done by either the local graphic screen or remote HMI screen. They must have the remote SCADA and local or remote manual switch operation in the equalization logic. The equalization logic is going to help us assure that the same circuit switcher associated to a particular capacitor bank is not used multiple times, while the rest of the circuit switchers associated to other capacitor banks are not used near as much. We're used to select the circuit switchers that was next in line to be operated. So we're going to operate these circuit switchers in some logical order, 1, 2, 3, then back to 1, for instance. And this is, once again, a very specific customer application. But hopefully by using some of these key logic keys, you'll be able to develop other applications that you might want to use. So with the automatic control and the logic we're going to look at is the narrowband or wideband voltage regulation. We're going to look at narrowband to wideband transfer logic, narrowband hunting and wideband transfer logic, wideband hunting and manual control transfer logic, and switch operation logic. And we're going to go through and see exactly what these mean and see how we can develop a logic for them. So what is narrowband or wideband voltage regulation? Here we're showing for a 161 system, if the bus voltage is between 163 and 165 kV, we're going to consider that to be some normal operation. Any voltage excursions above 165 or below 163 will initiate a narrowband condition. And similarly, with the wideband condition, any voltage excursions above 168 kV or below 161 kV will initiate some kind of wideband condition. So, narrowband operation. The idea here is showing you the capacitor banks opening and closing during voltage excursions above the narrowband realm. This is take an example that the relay is in, or the system is in narrowband mode, and you're going through at normal system voltage, and you drop below some predefined 27 NB or narrowband voltage, say below 163. The logic should then initiate some narrowband time. If that time expires, we are wanting to close a circuit switcher associated to a capacitor bank to try to stabilize system voltage. After system voltage stabilizes, it might exceed the desired voltage level. With that, it reaches a 59 NB or 59 narrowband. Once that narrowband is reached, a timer is associated with that. That timer expires. While still in the narrowband mode, we will open a circuit switcher to remove ours from the system. Similar to the narrowband operation, wideband operation works the same way. When you're in wideband mode, if the system's in wideband mode, and you go over a 59 wideband voltage level, you will start a wideband timer. This wideband timer expires. You will, for this instance, open a circuit switcher associated to a capacitor bank to remove ours from the system. When you're in wideband mode and your voltage goes above the narrowband mode, nothing will happen. It's an either-or condition, either in wideband or narrowband mode. So how is the logic needed to develop this wideband or narrowband voltage regulation? We do this through a function block called BNMMXU. This BNMMXU takes the bus voltage and can associate settings to that bus voltage with conjunction to a range expander to initiate binary outputs to define what mode the relay is in. And we're going to look at the settings associated to this MMXU to define these limits that will initiate and tell the relay what voltage excursion it's experiencing at that particular time. If the 59 wideband and 59 narrowband drive an over voltage condition and a 27 narrowband and 27 wideband drive an under voltage condition, these under voltage and over voltage conditions are what can initiate opening or closing of circuit switchers. So voltage regulation, how is it done? Here are the settings associated with the BNMMXU function block. Here, this is function block is a phase to ground function block. So, for instance, I have a setting here set for the high limit. This high limit is associated to the 59 wideband mode. If the phase to ground voltage goes over 96,995 volts, we will have the binary output 59WB asserted. This will then drive logic inside the relay, and you can take this high level to initiate timers and follow up with the logic needed to open up the circuit switcher. Similarly, if the voltage drops below 95,263 volts, the 27 wideband will be asserted and the associated settings with it. Dead bus detection. The need for dead bus detection is to supervise the 27 wideband function. The need for dead bus detection is if this capacitor bank falls on a radio line and the line is open. We don't want switching of the circuit switchers to happen during a deadline condition. This would bring a system condition maybe undesirable for the dispatcher when the dispatcher brings that line into service. The logic needed is an undervoltage element, which is shown here as a 27 UV. When this gets picked up, we can take this output to, say, AND gates with the 27 wideband function to block the desired function. Narrowband to wideband transfer. Shown here in the graph is a depiction of what narrowband to wideband transfer is. You start here in nominal bus voltage, and the relay or system is in the narrowband mode. So the narrowband timers associated with opening or closing are utilized. However, you have a large voltage excursion below the 27 wideband time. This might cause you to close circuit switchers faster because of the severe voltage drop you're experiencing. To do this, we are in narrowband, and we drop below the wideband 27 WB voltage. We can start a timer. This timer would then kick the system into wideband mode and use the wideband timers to close circuit switchers to add bars more quickly. So the logic needed for narrowband to wideband transfer is done by these three function blocks. I have an AND gate, a timer set, and a pulse timer. This AND gate is satisfied by if the relay sees that the wideband function has been initiated. If the relay is in auto control, so it is not a manual control and you want automatic control of the circuit switchers, and the relay is in narrowband by the manual switch. So the system's in narrowband and you go outside of the wideband voltage excursion, you will start a timer. This timer can be settable to your system needs. this timer expires, then we will have a transfer from narrowband to wideband. Hunting logic. Hunting is described by the open, close, open, or a close, open, close condition in the system of the capacitor banks. This is usually utilized when you have capacitor banks that are too big to stabilize the system voltage. Here we can see voltage going in its normal realm. It goes above the narrowband time, and we open up the capacitor bank. We then start a narrowband timer shown here at the top. If we have another voltage excursion below the 27 narrowband time, we get a close of a capacitor bank, and then followed by another open before this narrowband transfer time has expired. We have met the condition that we need to go from narrowband to a wideband condition. Similarly, wideband hunting. Narrowband to wideband went from narrowband and automatically switches the control scheme to a wideband operation. Wideband hunting automatically switches the scheme to a manual operation and discontinues all automatic control. Here we show going into the wideband time, similarly to the narrowband to wideband hunting scheme. We show an open, close, open condition. Here we have the open condition shown at number 1. We start the wideband hunting transfer time. If we see the circuit switchers close and open again, we will know that we are in a wideband transfer time situation, and we'll take the relay to normal or manual operation. Now we'll look at the logic needed to do both these schemes. Here is the conglomeration of AND gates, OR gates, and latch gates that I have put together to develop hunting logic and to determine if I need to make a hunting transfer decision. Here I have an AND gate driven by an overvoltage condition, and if the relay is in manual. If the relay is in narrowband by a manual switch, I will satisfy this AND gate. Start a timer. This timer is what I'm going to set my hunt time to be. So if I have an open, close, open before 65 seconds, I will drive to a narrowband to wideband transfer. I do this by a series of latch gates listed here by SRM memory function block. This memory function block is a latch gate that's picked up, and I have the overvoltage condition, having a circuit switcher open, and then driven to an AND gate that drives a second latch gate based on an undervoltage condition. I have an open, close, open condition by these two latch gates. If this condition is met, I have a narrowband to wideband transfer. These latch gates get reset if I have a 65-second time. So if I have an open, close, open past 65 seconds, these latch gates will be reset, and I will not have this AND gate driving the narrowband to wideband transfer logic. The other additional logic that I need for this capacitor bank is switch operation equalization logic. I need a way to define that each capacitor bank is utilized the same amount of times. I use that through this step function block. This switch open and close operations are handled independently. Only one switch is able to open or close on the next open or close switch command. An operation command, if selected, switch to open or close is not ready, then we need to skip that particular switch and go to the next particular switch in that order. A step is issued on a switch open-closed confirmation by a switch position. So how we do it in the relay. Here is our switch equalization logic. This SLGGIO drives 6 outputs. These 6 outputs associated to, for this instance, up to 6 capacitor banks, separate switches. Every time we ask the circuit switcher to close, this close equalization step is driven by the under voltage condition, or 27 or 59 wideband or narrowband. Once this is driven, it'll initiate a close step, whatever close is next in line to be activated. The switch has a memory, and it keeps up with what position is used. It stays in that position until it gets a closed equalization step. So if we are initiating a closed equalization step and it's circuit switchers 2 to close, we will get a closed step 2 into this AND gate. The only way this AND gate is satisfied is if any of these, if the circuit switcher is ready to do an actual close operation. How we supervise this close operation is by this OR gate. If this OR gate is picked up, we can determine that the circuit switcher number 2 is not available to operate. I drive this by these 3 wire tags. These conditions are if the circuit switcher is out of service, if the circuit switcher is just opened, you can set the circuit switcher just open can be set based on some time delay, knowing that certain capacitor banks must discharge their capacitance. If they have just opened, they sometimes need a time delay that would cause the circuit switcher not to be available, or if the circuit switcher is already closed, driven by the 89A contact. If the circuit switcher is not ready to close, this OR gate output can be driven to skip that particular circuit switcher and try to close step 3. If this OR gate is not satisfied, the in-out will be picked up, satisfying this AND gate and allowing circuit switcher 2 to close. Typical controls that you might find for this particular capacitor bank is the manual equalizing control. This gives you the ability as an operator to issue either an open or close command to the capacitor bank system, and then let the relay choose which circuit switcher is next in line to be operated. We have an auto manual condition. This allows us to bring the capacitor bank in automatic control or manual control. If you want your hunt detection turned on or off. And your operational band, your 43 band, this will drive if the system's in narrowband or wideband, and the narrowband to wideband transfer if you desire to have that functionality on. We also have the ability here, we show 3 circuit switchers connected to 3 capacitor banks. These circuit switchers are similar to how a circuit breaker is controlled. You can normally open or close these circuit switchers if you do not want to go through the manual equalizing control. And we have a switch that drives the in-out condition of these capacitor banks. Shown on the screen is all the capacitor banks in service. What would take these capacitor banks out of service was either a manual operation to that switch, taking that capacitor bank out of service, or a trip off your voltage differential element. So let's look at the manual switch equalizing control circuit and the logic that you'll need for that. To associate that manual equalizing control switch, we would have to add the additional logic of a VSG-GIO. We would tie this switch similarly as we showed tying it to the HMI screen. Activation of this switch, you can either close or open a circuit switcher. I would then drive the wire tags from its function block to 2 OR gates. These OR gates are driven by, shown, the manual equalizing control function block, or from logic developed from the 27 narrowband or wideband logic. This would define as an undervoltage condition, thus starting the equalization step to close a circuit switcher. And similarly, we have the open command coming from the DSG-GIO, which is our manual equalizing control switch, or the 59 narrowband wideband logic to define us an overvoltage condition, telling the selector switch that we need to open the next circuit switcher in line. All right, moving from the capacitor bank logic, we're going to look into another application called the line breaker bypass scheme. This bypass scheme, the transfer bank differential and bus bar differential protection is affected by which breaker is bypassed. The benefit of this substation layout is that any breaker can be bypassed at any time. And the drawbacks from this particular scheme is that the complex switching current scheme is needed. These protection schemes must be interlocked with which circuit breaker is bypassed. So to understand the scheme, we'll look at a generic single line of this particular application. We have a main and transfer bus shown with 3 breakers. We have 2 lines, and we have a bank/bus breaker shown here as 952. The benefit of this scheme is at any one time, any circuit breaker can be bypassed for either maintenance or taken out of service and keep the whole system intact. So during the normal operation of this scheme, and disregard the direction of the arrows, I'm just trying to represent the current flowing through the substation, we would have 989-5 open, 989-4 closed, 989-1 closed, providing current going through 952 onto the main bus through breakers 252 and 152 going out to the lines. Line disconnect switches 189-3 and 289-3 would be open as well to prevent current backfeeding to the transfer bus. Your CT91 showing just above the 952 breaker will provide your transformer differential coverage, and your CT-1 and CT-2 will provide your bus coverage. It's shown below of the breakers 152 and 252. During the bypass scenario, shown for example is if 152, PCB 152 is bypassed, we would open up our line disconnect switches 181-1 and 189-2, and we would close 189-3. This will provide us a disconnect for isolating breaker 152. Your path for current would be going through line 1 to the transfer bus and through PCB 952. Now your CT91, shown above PCB 952, will provide your distance protection for your line 1. Your CT92 and CT2 provides your transformer differential coverage. Here there is no bus coverage needed. Your circuit breaker 252 will be similarly bypassed. So we'll look at PCB 952 being bypassed. We would need to open up the disconnect switches associated to 952 by opening up 989-2 and 989-3. We would close disconnect switch 989-5, thus feeding the transformer directly onto the main bus. With this scenario, your CPs 1 and 2 associated to breakers 152 and 152, 152 and 252 will provide your transformer differential protection. And once again, as well with the line breakers being bypassed, there will be no bus protection needed. So the point we're showing this bypass scheme is that you're going to, in a traditional application, need a transfer switch done by a manual stacked switch, switching currents to provide the correct protection element its needed source. In this case, the positions are normal, bypass 152, bypass 252, and bypass 952 on your switch positions. This includes switching CTs to the correct protection zone, changing the 911 relay, usually through contact input, when bypassing a line breaker, and appropriately switching the 87B and 87T lockout circuit to meet the bypass configuration needs. This system requires a lot of wiring terminations, a large switch, comprehensive design, and installation efforts, considerable testing. Most of them can be eliminated if this current switching is done in logic. So the solution is develop the logic to determine what configuration the substation is in. Use the substation logic. Use the substation disconnect switch positions to develop interlock logic, and supervise with a virtual selector switch on the relay or the station HMI. So the logic used to develop this switching scheme. Shown in the gray box is a normal bypass 152, bypass 252, and a bypass 952 interlock logic. These interlock logic can be developed using the A or B fingers from the disconnect switches. Based on the interlock logic, you will be able to tell the system what condition the substation is in. With that, I can AND it with a selector switch. The selector switch can be used and toggled through either the local HMI or a station HMI. So when the operator believes he's in the correct position or a normal condition, he must go through this AND gate, and if the A and B fingers, based on our configuration of the system, agree, we will satisfy this AND gate, and we get positive acknowledgement that we are actually in a normal configuration based on the switch condition and station condition. If we are not in this particular configuration, if the switches and the actual system configuration do not agree, we can go to some error. Here is shown as the logic developed for the error alarm. If this error alarm goes off, this can give it, then drive either through DMP remote indication or ring bells or light up lights at the station. All right, logically, the line breaker bypass scheme. This is shown logically the virtual CT switching. The rules when you switch CTs in logic are different than actually using a hand-operated switch, is that you're able to open up CT circuits in logic without opening up the CT itself. You do not have that same condition when you're working with a hand-operated switch that actually physically opens up these current circuits. You would have to short the CTs out when you're not utilizing them. So in logic, if we have our normal condition okay, we would invert that, making that a 0, and not allowing it to block the current contributions from CT1, shown here in the top function block. This would then allow this function block to pass the CT currents from CT1 going to the bus differential, and as well passing the CT current contribution from CT1 to the transformer differential. How this is done in logic, the same condition is met. We have a normal condition. We will invert that logical 1 to a 0 and unblock the SMAI 2. This would allow the currents to pass through the SMAI block and continue on to the bus differential. The currents are virtually blocked when the system is not in the normal condition, so we no need to physically open any current circuits. Once we define that we are actually in the normal condition, or if 152 is bypassed and it's okay, or 252 is bypassed okay, we can virtually select what setting group is active. We do this by utilizing the active setting group function block. When this active setting group is picked up, for instance, if we're in the normal condition and it's okay, we will utilize settings in the relay associated with setting group 2. Similarly, if we're in the bypass condition of 152, we will utilize the conditions and settings of setting group 2. And if 252 is bypassed, we will utilize the settings associated with setting group 3. These benefits to the customer is a complex current switching scheme can now be easily addressed with the use of function blocks. These interlocks can be easily developed and verified with the use of function blocks to prevent system misoperations by applying an incorrect setting group to the relay, and switching currents virtually instead of using a gang-operated disconnect prevents opening up your current transformers. And I'd like to thank you for listening in. That's all I got. I know this is a shorter of the webinars, but I wanted to show you some of the key logics needed for the application shown, and hopefully you'll be able to build off these logics to your own system needs. And I thank you. And I turn it over to Tracy now. Or if there's any questions, feel free to type in the questions in the question box. Getting a question here. Where can we find the details of the capacitor bank protection and control? Could you give us your data in order to contact you? And it's interesting in those topics. I can talk to you the details about the capacitor bank. Once again, this is a particular application that was developed, and we show integration of that. But I'll be more than happy to talk to you more in depth of the logic. Just contact me at the email address shown at the beginning. My contact information, I'll move it to that slide. I can reach you. You can reach me there at j.b.hicks@us.abb.com. Is there any more questions?
Jay, can you hear me?
We can hear you now, Ms. Tracy.
Hey, sorry. I think that's it for today. Thank you all so much for your attendance, and you will receive your usual follow-up email tomorrow with a link to the recorded archive. And that's it for today.